What if the very ends of our cells, the bits that wear down, aren't really a fixed endpoint?
Mm.
Like, what if there's a way to influence that biological clock ticking away inside us? We all kind of feel things slow down eventually, right?
Yeah, that sense of cellular machinery getting, well, tired.
Yeah.
It seems inevitable.
But what if science, maybe even guided by some really ancient wisdom, could
Hmm.
point to ways to slow that down? Or maybe even turn it back a bit?
It's a huge question, isn't it? Really gets to the core of how life works. For ages, cellular aging looked like just a fact of life, unavoidable.
Right.
But the deeper we look, at the molecular level, the more we find these intriguing little points where maybe, just maybe, we can step in, often in surprising ways.
Exactly. And that's really what we're digging into today in this deep dive. We're focusing right in on those crucial bits at the tips of our chromosomes, the telomeres,
Telomeres, yes.
and this enzyme telomerase that apparently has this amazing ability to, well, interact with
A
them.
very special enzyme.
But here's where it gets really interesting, I think. We're also looking at how a traditional Eastern herb, most people know it as astragalus,
Hmm.
and a specific compound from it called TA65 might connect that ancient idea of vitality with cutting-edge science, especially thinking about healthy aging and immune function.
And to help us navigate this, we've got a couple of really solid sources. One's a scientific study abstract from PubMed, actually,
Yeah.
looking at TA65, specifically in folks recovering from a heart attack.
Oh, okay, real-world application there.
Definitely. And the other is a really insightful article that goes into the secrets of telomeres and this whole idea of K anti-aging focused on drag.
K anti-aging, interesting. So our mission, basically, is to unpack all this, get the key takeaways, understand the science of these tiny cellular parts, look at the, millennia of history behind drug use,
Yeah.
and then see what a modern clinical trial actually found about this compound. It's about understanding our cells' limits, sure, but also exploring if we can maybe, push those limits a bit.
Absolutely. So let's start right there, inside the cell nucleus, where our DNA lives, organized into chromosomes.
Okay.
And at the very, very ends of these chromosomes, we find these special structures, the telomeres.
Telomeres, right. The source used that analogy. I like the plastic tips on shoelaces.
That's a perfect analogy. They're made of these repeating DNA sequences over and over, and their job, protection.
Pure and simple.
Protection from what?
Fraying, basically, or
Yeah.
sticking to other chromosomes. They also stop the cell's repair machinery from thinking the end of the chromosome is actually damaged DNA that needs fixing, which could mess up the important genes inside.
Ah, okay. So they're like the essential buffer zone.
Yeah.
Keeps the important genetic information safe and sound.
Exactly, a protective cap. But, and this is the big but, this is where the aging connection comes in. Every time a cell divides, which happens constantly for growth, repair, all that stuff,
Mm-hmm.
the machinery that copies the DNA, it can't quite copy the very, very end bit of the telomere. Oh, so with every copy, the telomere gets a tiny bit shorter, the shoelace tip wears down a little.
Precisely. A tiny piece gets lost each time. And this gradual shortening, this is really a fundamental marker of cellular aging.
Okay.
As those telomeres get shorter and shorter, eventually they hit a critical length. And that signals to the cell, okay, you've divided too many times.
And then what? Does it just stop?
It enters a state called replicative senescence. Basically, yeah, it stops dividing.
Senescence. Sounds final.
It kind of is. For division, anyway.
Right.
These senescent cells often don't die right away,
Mm.
but they stop replicating and they don't function as well.
Mhm.
Sometimes they even hang around secreting inflammatory stuff, which isn't great for the surrounding tissue.
Right, that contributes to that overall feeling of aging, the decline.
It's a major factor. So the key thing here is that cellular aging isn't just some vague wear and tear. It's tied directly to this measurable biological clock, the length of the telomeres. Our physical aging is definitely linked to our cells hitting this senescent state.
Wow, okay. That makes it very concrete. The telomere shortening is the clock ticking. But you mentioned earlier there's something that might interfere with this. An enzyme.
Yes. And this discovery back in 1997 was huge. Nobel Prize-winning work by Elizabeth Blackburn and her colleagues. They identified an enzyme called telomerase.
Telomerase. Okay, the name sort of gives it away. It makes telomeres.
It does exactly that. Telomerase has this incredible ability to add those repetitive DNA sequences back onto the ends of the telomeres.
So it can counteract the shortening?
It can literally rebuild them, yes. Which means, in theory, it could extend the number of times a cell can divide before it hits that senescence wall. It could lengthen its replicative lifespan.
Okay, hold on. That sounds amazing. Like, could it make cells just keep dividing forever? A cellular fountain of youth?
Well, that's the multi-billion-dollar question, isn't it? And where the biology gets tricky. In humans, telomerase isn't just on all the time in every cell. It's very tightly controlled.
Ah, okay. Where is it active then?
It's highly active in cells that need to divide a lot, like embryonic stem cells, obviously building a whole organism, and also in some adult stem cells that handle tissue repair.
Makes sense.
But in most of our regular adult cells, the ones making up our organs and tissues, it's largely switched off, or at least the activity is very, very low.
And there's a downside risk too, right? You mentioned cancer?
That's the major concern, yes. Cancer cells often find ways to switch telomerase back on. That's part of what allows them to achieve immortality, in a sense, and divide uncontrollably.
Okay, so the huge challenge for science is figuring out if we can activate telomerase just enough in the right cells to get the benefits for healthy aging and repair.
Without accidentally giving rogue cells the green light to become cancerous. It's a very fine line.
And this is where that ancient herb comes back into the picture?
Exactly.
Yeah. Oh.
This modern scientific puzzle, how to influence cellular lifespan, actually finds this really fascinating echo in traditional medicine. The sources really highlight or Astragalus, which has been used for, well, thousands of years in Korea and China.
Yeah, I think I've heard of Astragalus, usually for like immune support or as a general tonic.
Its traditional uses are incredibly rich, and they really point towards this idea of enhancing vitality or life force. In traditional terms, it was used to boost ki.
Boost ki.
Ancient Korean medical texts like Dongyubogum talk about using it to strengthen the body, fight weakness, protect organs, deal with chronic fatigue. Some formulas with it were even called the king of tonics.
Wow, king of tonics.
What?
So the intuition was definitely about boosting overall energy and resilience.
Absolutely. People felt it made them stronger, more vital.
So how did we get from that ancient observation, that feeling of vitality, to the molecular stuff we were just talking about, telomeres and telomerase?
Well, modern science started digging into what exactly in the Astragalus root might be causing these effects. Researchers began isolating and analyzing its chemical components, and they identified a key molecule, a saponin, called cycloastragenol, often abbreviated as CAG.
Cycloastragenol, CAG. And that's related to the TA65 you mentioned.
Yes, exactly. TA65 is essentially a highly purified, concentrated extract derived from that cycloastragenol found in the Astragalus root.
Okay.
And this TA65 really started getting attention internationally, marketed as a supplement aimed at telomeres. That spurred more research into its actual effects, especially on human immune cells.
So the traditional idea of boosting vitality might actually be explained by this specific molecule interacting with these really fundamental cellular processes.
That's the exciting possibility, yes. And the research suggests TA65, or CAG, might do more than just affect telomere length directly. The sources indicate it has a broader impact on the cell.
Broader how? What else does it do?
Well, besides studies showing it can increase telomerase activity in immune cells and help stabilize telomeres, maybe delay senescence in lab settings.
Which is already pretty significant.
Absolutely. But beyond that, the sources suggest CAG might influence gene expression.
Gene expression? You mean like telling the genes which ones should be active or inactive?
Precisely. It seems to interact with the cell's epigenome. If you think of DNA as the hardware, the instruction manual, the epigenome is like the software layer on top. It controls how those instructions are read and used.
Okay.
So CAG might be subtly reprogramming that software, maybe nudging cells towards a more useful or functional pattern of gene activity.
Wow. That's way beyond just adding length to the telomere cap.
It is. And there's more. It also seems to play a role in regulating autophagy pathways.
Autophagy. That sounds familiar but complex.
It's basically the cell's housekeeping system. Its way of cleaning out old damaged parts, proteins, organelles, other junk. It recycles them. It's crucial for keeping cells healthy, especially under stress.
So CAG might be boosting the cell's internal cleanup crew.
That's a good way to put it. And it also seems to activate antioxidant networks within the cell.
Helping fight off damage from free radicals and oxidative stress.
Exactly. Helping bolster the cell's defenses.
Okay, so let me see if I've got this. It's potentially influencing the master control system, the epigenome, the recycling plant autophagy, and the defense shield antioxidants.
That's a fantastic summary. It seems to be influencing several key systems that maintain cellular health and resilience.
And this could provide a real molecular explanation for why people traditionally felt dry boosted their vitality. What they felt as more life force was maybe the result of all these cellular processes working better.
That's the hypothesis, yes. A convergence of ancient empirical wisdom and modern molecular discovery. It's quite profound when you think about it.
It really is. So moving from the lab bench and traditional use to a real-world situation. You mentioned that study involving TA65 after a heart attack. Can you walk us through that one?
Sure, it's a really relevant study because it looks at TA65 in the context of both aging and a major health event. We know that a heart attack, a myocardial infarction, or MI, does more than just damage heart tissue.
Aye.
It can actually accelerate aging of the immune system. It's a process called immunosenescence.
Immunosenescence.
Okay. This often shows up as a decrease in the total number of immune cells, lymphocytes, that's called lymphopenia, and also an increase in certain types of older, less effective immune cells. One specific type they focused on are these CD8 plus T cells, called Telomerase cells.
So basically, after a heart attack, your immune system gets older, faster, and maybe less effective.
That's the concern, yes. It can leave people more vulnerable. So this study wanted to see if TA65 could help push back against some of those negative immune changes in people who'd had an MI.
How did they set it up?
It was designed as a double-blind, randomized controlled pilot trial, which is, a strong study design.
It's old standard, yeah.
We took 90 elderly patients, all over 65, who had recently had a heart attack. And for 12 months, they randomly assigned them to get either 16 milligrams of TA65 each day, split into two 8-milligram doses, or a placebo, a dummy pill.
Okay, 12 months. And what was the main thing they were hoping to see change?
Their primary endpoint, the main goal, was to see if taking TA65 would reduce the proportion of those specific aged immune cells, the CD8 plus Telomerase lymphocytes, after the year was up.
Did it work? Did it lower the percentage of those cells?
Interestingly, no. The study found that for the primary endpoint, the proportion of CD8 plus Telomerase cells, there was no statistically significant difference between the group taking TA65 and the group taking the placebo after 12 months.
Oh, okay. So it didn't directly reverse that specific marker of immune aging they were targeting first.
Not according to this specific measure in this trial, no.
But were there other effects? You mentioned secondary outcomes.
Yes, and this is where things get quite interesting and positive. This study did find a statistically significant increase in the average total lymphocyte count in the group taking TA65.
Total lymphocytes. So the overall number of immune cells went up.
It did. The estimated increase was about 285 cells per microliter compared to their baseline. And crucially, this increase wasn't just in one type. It was seen across the board in T cells, CD3 plus, CD4 plus, CD8 plus, B cells, and natural killer cells.
And the placebo group didn't see this increase.
No, the placebo group showed no such increase. So even though the proportion of that one aged cell type didn't change significantly, the TA65 group ended up with more overall immune defenders circulating in their blood.
That seems really important. More soldiers in the army, even if the age distribution didn't shift exactly as hypothesized.
It's definitely a positive finding, especially in an elderly population recovering from an MI. More immune cells generally means better capacity to fight infections and handle other challenges.
Makes sense. What about inflammation? They measured hsCRP, right?
Yes, and that was another key positive result. After 12 months, the levels of hsCRP, that marker for systemic inflammation, were significantly lower in the TA65 group compared to the placebo group.
How much lower?
About 62% lower on average. The TA65 group had an average hsCRP of 1.1 milligl versus 2.9 milligl in the placebo group. That's a substantial reduction in inflammation.
Wow. Okay, so boosting overall immune cell numbers, A and D, significantly cutting inflammation, those sound like really valuable benefits for these patients.
They are indeed. And one more thing the study noted. Patients taking TA65 reported significantly fewer adverse events overall during the trial compared to the placebo group.
Fewer side effects, too. That's also important. So summarizing the study, didn't hit the primary target on the proportion of that specific aged cell, but did show significant improvements in total immune cell counts and a major reduction in inflammation, plus fewer adverse events.
That's a fair summary of the findings reported in the abstract, yes. And this whole story, really from the ancient use of A for vitality to identifying CAG to TA65 and now testing it in rigorous trials for conditions linked to aging like post-MI immune decline, it's incredibly symbolic, don't you think?
Symbolic of what? Bridging the old and new.
Exactly. It shows how traditional knowledge, built up over centuries of human experience and observation, can provide these incredibly valuable starting points. Leads that modern science, with genetics and biotech tools, can then investigate, refine, and potentially turn into new therapies for aging and the diseases that come with it.
Translating ancient wisdom into modern medical language.
Precisely. And the sources we looked at actually suggest Korea might be in a unique position to lead in this area.
Oh, really? Why Korea specifically?
Well, the article points out a few things. Korea has native varieties of breed that are apparently known for having high levels of active compounds, like saponins. Plus, there's the incredibly deep, well-documented history of traditional Korean medicine. The know-how is there.
Right.
Then you combine that with Korea's strong modern biotechnology sector and this growing global recognition through the K-Health or KBO brand. It's like having the raw materials, the historical knowledge, and the modern scientific engine.
It does sound like a powerful combination for driving this kind of research forward.
And the potential might not just be in single ingredients. The sources hint at future directions involving synergy.
Synergy, like combining things.
Yeah, the idea that Ray's effects might be even better when it's part of a carefully designed traditional formula, maybe with other herbs like Korean red ginseng. Or, looking really cutting edge, combining it with modern compounds like NAD+ boosters.
NAD+, I keep hearing about that in aging research too, something about cell energy and repair.
Exactly. NAD+ is vital for cellular energy production and repair pathways involving things like SIRT1 and AMPK. These are other key cellular managers that tend to decline as we age.
Okay.
So the thought is, maybe you could target multiple aging pathways at once. Combine something like TA65 for the telomere aspect with something that boosts NAD+ levels to support SIRT1 and AMPK activity, creating a kind of multi-pronged attack on cellular aging.
Like a team approach inside the cell, targeting different key pathways.
That's the idea. Moving beyond just one target to a more holistic strategy for maintaining cellular health and function. It's about seeing traditional wisdom not just as history, but as a living source of leads that can be integrated with the very latest science.
Okay, so let's try and wrap this up. We started this deep dive looking at the absolute ends of our chromosomes, the telomeres.
And how their shortening acts like a cellular clock driving aging.
Then we met telomerase, the enzyme, with that amazing potential to rewind the clock, at least partially, by rebuilding telomeres, though controlling it safely is key.
Right. And then we journeyed back centuries to Astragalus, traditionally used for vitality.
And saw how science zoomed in on TA65, a compound from it, which seems to do more than just influence telomeres. It affects gene expression, cell cleanup, antioxidant defenses.
Giving a potential molecular basis for that traditional idea of vitality.
And finally, we looked at that real-world study. TA65 after heart attack didn't change one specific cell ratio, but it significantly boosted overall immune cell numbers and lowered inflammation.
Demonstrating tangible benefits in a vulnerable group.
It really feels like a full circle. From the microscopic DNA ends to ancient knowledge to modern trials, it suggests that maybe the end of the cell, the telomere, isn't so final. Maybe it's a place we can learn to influence, to enhance our vitality.
It definitely opens up possibilities. And it makes you wonder, doesn't it, how much more untapped potential is sitting there in traditional medicine systems around the world.
Yeah.
Practices refined over countless generations, holding clues to complex biology that we're only just starting to unravel with our modern tools.
So here's something to leave you thinking about. How many other ancient remedies or traditional practices are out there, maybe overlooked, just waiting for their scientific translation? Waiting for us to connect the dots between traditional wisdom about health and the modern language of genes, proteins, and cells? What other keys to our future health might be hidden in the insights of the past, ready to be rediscovered?